Hello, everybody. You all look lovely today. My name is Breanna Devore-McDonald, and I am a PhD student at UMass Amherst. This is joint work with my advisor, Emery Berger, and today we are talking about attacking plagiarism detectors. To do that, let me introduce you to Chet. He is an undergraduate computer science student, and he's in data structures with 200 of his peers. His university is just like any other good university, so let's say he goes to Stanford, where 20% of computer science students have been caught plagiarizing their code. Or maybe he goes to UC Berkeley, where the same percentage of computer science students also have been caught plagiarizing. Or maybe he goes to Brown, where 70% of cheating incidents were in the CS department. Or maybe he goes to any other of these big name universities because the story is always the same. But catching cheating is a hard problem. The number of CS enrollments has skyrocketed in the last decade, and manual inspection is O of n squared, so it doesn't scale. It worked when there were 10 students in a classroom, but now there are hundreds. And there's usually a small cap on the number of TAs per 200-person course, and each is employed for 10 to 20 hours per week. So we actually surveyed a group of computer science instructors and found that 65% spend less than 10 minutes in total on each individual assignment. So that includes grading and plagiarism detection. And they're definitely not manually inspecting every n squared pair of assignments. And as a result, there is a heavy reliance on automatic plagiarism detection tools. For example, we found that 70% of instructors use these tools. And what's really interesting is a little over half of our respondents say that they manually inspect 0% of their coding assignments. And the other half rely on plagiarism detectors to inform which assignments to even look at. And you can read more about our surveys in the paper. And a major reason professors feel comfortable relying so heavily on these tools is it's widely assumed that plagiarism detectors are difficult to evade. The working assumption is that it would take more time and energy for a student to fool a detector than it would to actually do the assignment. And even the author of Sherlock, which is a popular plagiarism detector, says that he doesn't worry about students fooling detectors because that means they probably program at a good standard already. So let me introduce you to the professor of this talk. And he's experiencing the same thing I just described, and he has the same working assumption. And he has a really bad nightmare. And his nightmare, his suspiciously named student Chet, can turn in assignments where he actually did zero work. He doesn't even know the programming language they're using. And he didn't even pay someone online to do the assignment for him because he's a poor college student. And none of the plagiarism detectors available online can catch Chet's cheating. But it gets worse, as it isn't just Chet that can cheat without detection. It's his entire suspiciously named fraternity. Chet can conspire with all of his friends, and the professor can't catch any of them. Unfortunately for the professor, I need to give him a wake-up call because his nightmare is actually real life, and it's my fault. Because I've created a system called Mossad that lets Chet do exactly what the professor fears most. Mossad can automatically take a completed assignment and generate a new semantically equivalent variant that completely evades detection by every single plagiarism detector that's available online. And in fact, Mossad can generate dozens, if not hundreds, from a single base file, which is what allows Chet's entire fraternity cheat. And when you compare any of these Mossad files to its base file, using any plagiarism detector, not a single detector will tell you that these files have been plagiarized. And on top of that, when you compare all the Mossad files together, the plagiarism detectors will also report that they're not been plagiarized. And on top of that, in case of a spot check, which is unlikely because Mossad works really well, regardless, the TA will not be able to distinguish Mossad files from authentic files. And we did an empirical study of this that you can see later in the talk. So the rest of the talk is outlined as follows. I'll first talk about plagiarism detectors and how they work really well. And I will then talk about Mossad and how it's completely able to destroy them regardless. And I'll give you some hope for the future. So the professor of our talk uses Moss as his plagiarism detector of choice, which is what we're going to discuss in this talk. For the details of the other detectors, you can check the paper. Moss is a system for detecting software similarity. You can use it on any number of files and it returns similarity scores for each pair. For example, here, the similarity score is 99%. And you can look into it further. Moss actually color coordinates the matches, the code matches, so you can actually see which lines it deems similar. Moss works in a series of a few short steps that I'm going to tell you about. First, for every file, it will normalize them by naming all the identifiers to the same thing. It'll remove white space and comments. And the resulting code gets sent into the tokenization engine, which further normalizes the program. And the set of tokens get turned into a fingerprint. And this is where plagiarism detectors diverge. JPLAG and Sherlock use string tiling to create fingerprints, but Moss just hashes every overlapping n-gram, and the size of n depends on the source language. So this would be the example fingerprint for the file. And the fingerprinting engine also includes something called winnowing, which allows Moss to scale, but for the sake of time, we're not talking about that today. So Moss performs this on every single one of the professor's inputs, and it will directly compare the hashes of each file. And that's how it finds matches, and that's how it assigns a similarity score. So for example, the similarity score here is 40%. And again, not every plagiarism detector works in this manner. They all have some form of fingerprinting, which is the key takeaway here. So this Fibonacci program is actually Alice's. She is the smartest person in the classroom I mentioned earlier, and Chet steals her code, but he wants to try to hide his plagiarism using common techniques that you've probably seen. That includes adding and removing comments. He renames identifiers to something only he would think of, and just, in case he wants to remove the white space. But our professor is using Moss, and Moss compares these two assignments and actually gives it a 96% similarity. And in fact, when you actually inspect it, every single line Moss deems as the exact same. And Moss is widely used because of this. It does a fantastic job at detecting typical plagiarism cover-ups. It also can detect code rearrangement, and also it's really good at detecting obfuscation. So if you were to send your code into an obfuscator and then send the result to Moss, it would still give you a near 100% match. And so let's circle back to how Moss works. The very heart of the algorithm is that matches come from hashes, which is the core concept that Mossad attacks. So if you ensure that the hash values never collide, then you'll always get a 0% match. So let's work backwards from the hashes. So from those hashes, we get this window of source code. And the central idea of Mossad is to disrupt this fingerprint window, which can be done by just adding a variable declaration that gets optimized away. So Chet employs Mossad's basic technique and inserts 3 variable declarations to Alice's assignment. They get optimized away. And Moss actually gives this a 0% similarity score when the whole entire file was the same except those 3 extra lines. But let's say the TA chooses for this to be spot checked. The challenge is now, is this distinguishable from authentic student code? And on top of that, if more than one student does the exact same thing with Alice's code, there's going to be collisions. So for this, we take a page out of the book of GenProg. The next core concept of Mossad is that it randomly inserts lines of code from within the file itself. So Chet employs this, and he changes those 3 variable declarations to lines that exist in the original program, which was written by Alice. So every single line in Chet's program has been written by a student. And still, Moss gives this a 0% similarity score. So I already gave you the system overview of Mossad, but as a reminder, it is a source-to-source translator. It takes in a compilable source file, and it produces a semantics-preserving variant. It also takes in a target Moss score, or any plagiarism detector score threshold, and we surveyed professors to see where this line is that they deem not suspicious versus suspicious, and it was about 30%. but we were conservative and went down to 25%. So this is the target score, the target low score that a Mossad file needs to reach when compared with the original. And 25% is also lower than the average Moss score of authentic code. So Mossad is like simplified genetic programming. So the source file acts like a pool of lines of code, and our generation engine is broken into two parts. The first is selection, which takes a line from the pool. And the mutation engine creates a copy of the source file and tries to insert that selection somewhere. And it checks if they're semantically equivalent. The oracle that we use is compiling with optimization and then comparing the object code to see if it's the same. But you can use a different oracle. So this is not the only Mossad attack, it's just a framework. The other check that it does is to see if the Moss score has been met. And if either of those aren't true, then it just keeps doing this, saving the changes as they work. And Mossad can complete an assignment in under 5 minutes. So this is a larger real example from an assignment I wrote in undergrad. The left is the original and the right is the Mossad-generated. And so every single line is the same except for these 6 lines, which all came from elsewhere in the program. And when you compare this with Moss, you still get a 0% similarity score. And as a reminder, every single line of code from the disguised version exists in the original. So here are the research questions we have around Mossad. Can it produce variants that yield unsuspicious similarity scores? Can it enable mass plagiarism? Can it produce code that's no less readable than authentic code? Can it work no matter what the input size is? Is execution time low enough? And is it equally effective as other plagiarism detectors? And not to spoil it, but the answer is yes to all of them, but we're only going to go over the first 3. So I've already told you and shown you that Mossad can produce files that yield low Moss scores, but this is how we found that. We actually did a study on real student code. There were 3 corpuses in C, 200 students for each, and they were all around 175 lines of code, and they ranged in difficulty. And we randomly chose files to be used as input to Mossad, and then created the Mossad files, and then added those resulting files back to the corpus, and then compared it all with this. And we found that 100% of Mossad files score less than the average authentic score, and 100% score less than the threshold of suspicion. And the other 2 corpuses look the exact same. For our next research question, we wanted to know if Mossad enables mass plagiarism, which is what we saw with Chet's fraternity. And so we randomly chose 5 assignments to be used as base files, and for each we generated 30 Mossad variants. And we compared all of those with each other with Moss and found that over 90% score less than the 25% threshold, and 100% are under a 30% similarity score. So yes, Mossad enables an entire class to cheat a single student. Lastly, we empirically evaluated if Mossad code is distinguishable from authentic code, because our survey informed us that there is in fact a chance that these are spot checked. So we ran an experiment in a course for TAs and asked them to grade 10 assignments, which included authentic code, student code, and just 1 obfuscated code as somewhat of a baseline. And we asked TAs to grade based on program design and code readability, and we gave them a detailed rubric. We didn't want to lead them to any specific conclusion. So the open-ended question we asked them was, is there anything you think the instructor should know? And what is your overall impression of the code? And the first interesting result is that not a single TA reported anything suspicious. And secondly, we measured the effect size between Mossad population and the authentic population, found it to be small. In contrast, for the obfuscated code, it was a very large effect size. But this is not game over for plagiarism detectors. So we have a partial countermeasure. We think it should be deployed when possible, but it's not a perfect solution. So it relies on the oracle that we use for Mossad. So the idea is to compile every assignment to assembly and then compare the assembly with Moss. And we found that Mossad files similarity score this way shoot up to around 80%, and they're very noticeable. But like I said, it only works when the oracle is compiling with optimization. We have some other suggestions that are naturally plagiarism resistant, but they require more time and energy. So, like code review and integrating GitHub into your grading workflow, monitoring commits is a good way to catch cheating, but also they both have good pedagogical benefits as a side effect. So, your takeaway I want you to leave with is that plagiarism detectors are fundamentally flawed. Our attack defeats every available plagiarism detector that we could find. And these issues with Moss and other detectors suggest that we should be looking into how plagiarism detector works. It's focusing right now on syntactic detection, even ASTs, and we need to move past this. And we need to reevaluate our reliance on these tools. And we definitely need more research into this area. And I hope that is what you take away. Thanks.